continue to stand by. Your conference will begin momentarily. Today's call is also being recorded. If you have any objections, you may disconnect at this time. Again, please continue to stand by. Your conference will begin momentarily.
Hello, everyone. Thank you for joining us for today's media teleconference. My name is Elise Fisher. I'm with NASA's Office of Communications. And today we're here to discuss NASA's first test of high bandwidth laser communications beyond the moon. This technology demonstration is called Deep Space Optical Communications, or DSOC, and it's set to launch on October 5th aboard the Psyche spacecraft, which is the agency's upcoming mission to a metal asteroid. So ahead of launch, our speakers today are going to tell us a little bit more about DSOC, the goals of this tech demo, and some of the benefits of laser communications that could be used in future NASA missions. So with us on the line today, we have Tanya Laughinghouse, Program Manager for Technology Demonstration Missions with NASA's Space Technology Mission Directorate, Jeff Volosin, Acting Deputy Associate Administrator and Program Manager for Space Communications and Navigation for NASA's Space Operations Mission Directorate, A.B. Biswas, DSOC Project Technologist with NASA's Jet Propulsion Laboratory, and finally, Meera Srinivasan, DSOC Ground System Product Delivery Manager and Operations Lead, also with NASA's Jet Propulsion Laboratory. We're going to hear briefly here first from each of our speakers, and then we will take questions from those who are listening on the phone lines. So when we get to that point, you will be able to ask a question by pressing *1. But first here, I will turn it over to Tanya Laughinghouse to start us off. So please go ahead, Tanya.
Thank you, Elise, and good afternoon, everyone. Thank you for joining us today. Again, I am Tanya Laughinghouse, Program Manager for Technology Demonstration Missions, or TDM, within NASA's Space Technology Mission Directorate, or STMD, at NASA headquarters. Our TDM program office is hosted at NASA Marshall Space Flight Center. So on behalf of NASA STMD Technology Demonstration Missions Program, as well as our partners in the Space Communication and Navigations Program and the DSOC project team representatives from NASA JPL, all of whom you'll hear from today, I think it's safe to say we are all very excited about the upcoming launch of the Deep Space Optical Communications Demonstration Payload. We have been working on this technology project for a while now, and we are more than ready to see this capability go to its demonstration phase. The goal of this demonstration is to take optical communications beyond the Earth-Moon system to the next frontier, demonstrating high-bandwidth laser communications in deep space. Specifically, DSOC will test how lasers can improve the rate of data transmissions far beyond the capacity of current radio frequency systems used in space. And this will be, we expect this to be another step towards the progress that will help support our next giant leap, which is when NASA sends astronauts to Mars. There are more missions than ever headed for deep space, and they're expected to transmit huge volumes of science data and complex measurements, including high-def images and video, significantly increasing the bandwidth that's required. So experiments like DSOC will play a crucial role as a first-of-its-kind demonstration in deep space and helping NASA advance communications that can be used routinely and operationally by spacecraft and ground systems in the future. STMD's focus is on the importance of continued investments, which provide significant benefits to our nation's society and economy. STMD's mission is to drive innovation, advance technology that opens greater partnerships with industry, academia, and small businesses, while lowering the costs for other government agencies and commercial space activities. Technology demonstrations are by their nature very lengthy processes that progress through multiple stages. And because of that iterative process, it can take us a while to get to a point where NASA can take smart risks to fly and demonstrate new technologies in space, which is the environment they're expected to operate in. We expect to glean a lot from these tests and demonstrations that use that data for the next version of technologies to get them on the path to operational use. That is a huge win for us because they serve to reduce risk, to prove out concepts, and to improve the state of the art. We really couldn't get many of these space technologies to operational status without programs like TDM. And ultimately, the goal for our tech demo missions like DSOC is to be infused in future missions. So DSOC will launch as a hosted payload aboard the Psyche mission, which is NASA's first to a metal-rich asteroid, also called Psyche 16, and using DSOC's near-infrared laser transceiver, which is a device that can send and receive data. It will test high data rate laser communications with Earth during the spacecraft's journey to the asteroid belt. It will demonstrate operations nearly 2 years after the Psyche mission launch, and during that time, the transceiver will communicate with 2 ground stations in Southern California. And it will test out sensitive detectors, powerful laser transmitters, and various methods to decode signals that the transceiver sends from deep space. DSOC will make 1 contact per week for the duration of the technology demonstration. DSOC is really a natural extension of the experiments in laser comm that have come before it, and you will hear about those shortly. But by flying DSOC, we will gain valuable insights into how the technology works in space and how it can be applied in the future. And really, that's why we test, to advance innovation, all the while decreasing risks for future missions. And other technology demonstration missions have done the same. The Lofted experiment, for example, was a partnership between NASA and ULA, which we successfully demonstrated a new inflatable heat shield design that can slow down spacecraft to survive atmospheric entry. That launched November of 2022, and that technology has applications for a variety of proposed missions to destinations such as Mars, Venus, Titan, as well as a return of assets to Earth. Additionally, you may have heard in the news that we just completed our 2-year-plus oxygen-producing experiment on Mars called MOXIE aboard the Mars Perseverance rover. That TDM mission was the first ever experimental extraction of a natural resource from another planet for potential use by humans. And this technology can be scaled up for use in a human mission to Mars to provide breathable oxygen, oxidizer, and propellant for the return to Earth. So in closing, I'd like to say that we in STMD and TDM love to say that technology drives exploration. And we say it often because we absolutely believe it. Whenever we launch a TDM project, and we have launched 7 tech demos to space since 2018, what we in the program, we like to call that having their day in the sun. When we launch these technology demonstrations, we believe we're advancing capabilities for space exploration and promote America's global leadership in innovation and transform the world around us. So we are 15 days from the opening of the launch window on October the 5th, and I look forward to the new frontiers that DSOC will help us reach. So at this time, I'd like to pass it over to Jeff Filoson of NASA SCAN, who we are very proud to partner with in sponsoring DSOC. Jeff?
Thanks, Tanya. And yeah, thank you for the introduction. And from the space communication side, we're really proud, and this has been a great partnership with the Technology Mission Directorate, and so we're excited for the launch as well. And for my part, I represent the organization that is the core of the operations of all of the radio frequency antennas spread throughout the world, both commercial and government-owned, that we use to communicate with astronauts in space, and that we use to communicate with all of the probes that we send throughout the solar system, and even in some cases beyond. So for 60-plus years, we've been building bigger, more complex radio wave antennas on the Earth and in space to allow that communication so that you could see beautiful images from Hubble or hear the astronauts talking from the space station back to Earth or all kinds of applications. But, you know, as we've been evolving radio communications over the years, you'll notice that things like the size of the antennas we need are getting bigger and bigger. If you've ever seen pictures of 70-meter diameter antennas that we have spread throughout the world to communicate with probes out into deep space, radio waves do have limitations. And so our interest is for many applications to look at optical as a way to provide just like higher bandwidth internet on Earth. We're looking to increase the speed at which we can get data down to Earth, and we're looking to increase the amount of data we can get down to Earth. And that has a lot of advantages for us. So if we can leverage optical communications for a lot of our missions, we can allow them to get more imagery down to Earth more quickly so that we can get information not only about our Earth, but about the rest of the solar system and beyond. It could allow us to enable astronauts on the moon to be able to send back real high-definition imagery in real time from the moon. So we see a lot of different applications for this technology going forward, and it has a lot of advantages that we haven't been able to, radio waves just have limitations that we won't be able to use them for. So we will continue to use radio waves for many of our missions, and many of our missions can still use that part of the spectrum, but these optical technologies are going to be key to a lot of our future exploration, and as Tanya said, for enabling missions to Mars with humans and things like that. So the other thing about radio wave communication is that because it utilizes larger waves to send the data back to Earth, the beam has less energy when it comes to Earth, and so you'll see these really big dishes on the ground. So one of the things about optical communication, and you'll see it on the Psyche spacecraft, is there is a large radio antenna, and that's the primary way that Psyche will communicate back down to Earth, and then a large antenna on the Earth to capture that signal. For the DSOC experiment, you'll see a much smaller aperture that we'll use as a telescope to beam the signal from the satellite. And you'll see on the Earth, there'll be smaller telescopes to be able to catch that optical signal back at Earth. And so one of the big advantages for us is that the infrastructure that we need, both on the spacecraft and on the ground to do optical communications, shrinks down. That's easier on the spacecraft designers. It's also easier for us on the investment side on the Earth to be able to build smaller terminals that are more capable than any of the radio antennas that we have today. DSOC is key to our ability to communicate with optical communications outside of, as Tanya mentioned, the orbit of the moon, going out into deep space. But it's not the first and only time that we've experimented with optical communications in space. And so we started 10 years ago. So in 2014, if everybody remembers the LADEE spacecraft, the Lunar Atmospheric Dust Environment Explorer, that experiment or that spacecraft went to the moon. It carried along with it an optical communication demonstration. And that optical communication demonstration was a way to see how high a data rate could we achieve sending an optical signal back to Earth from the moon, and could we accurately point that system so that we could communicate. And that was a real big success. We achieved 300 megabits per second. And it opened up this idea of, hey, maybe we could go even further out into space and leverage this incredible technology, and that's what DSOC will do for us. Closer to Earth, we're also looking at the use of optical communication to enable new users in Earth orbit. So as we want to study our planet in more detail, we'd like to use cameras that can collect all kinds of sophisticated information about our environment. We're collecting more and more data. To get that data back to Earth, we're going to need, again, high bandwidth capability and optical comm and provide that for us. And so we currently have on orbit, in geostationary orbit, the Lunar Communications Relay Demonstration Satellite, and it provides an optical link where a satellite in low Earth orbit could send a laser signal up, and then it gets sent back down to Earth so that we can communicate from Earth orbit using lasers and then get that signal back to Earth. In the next few months, you'll see being loaded into SpaceX Dragon, an experiment called Illuma-T. Illuma-T is going to go up to the space station. It's an optical communications demonstration. It will be put onto the GEM experimental module, and it will communicate from space station up through our optical relay satellite and back down to Earth, all using laser communication. Again, we're looking at ways to increase the bandwidth for not only deep space applications, but for near-Earth applications using this incredible technology. And the last one I'll mention is, if you tune in when the Artemis 2 mission flies in a short time now, the Artemis 2 mission will be carrying another optical comm experiment called O2O, and that experiment is to focus on using optical communication between the Orion spacecraft to get high definition data, or high definition TV and high data rate data back to Earth from Artemis 2. And so we're really looking forward to that. So you can see that the application of this technology is broad. Each one of these demonstrations is playing a key role in advancing our knowledge about how to apply this to get all the benefits of high bandwidth communication using lasers, and to kind of hone in the technology so that it's directly, on the next set of missions, we can directly apply it operationally. So each one of these steps gets us closer to getting to operational laser communication. We're excited about this opportunity because it's really going to open up the outer solar system to bring back lots more imagery and lots more data as we learn more about how to communicate to deep space with optical. And it paves our way for someday having astronauts on Mars being able to send back high data rate data as well. So with that, I'm going to go ahead and pass off to Abe Biswas. And so Abe is going to give you a little bit more specifics about the mission of the DSOC mission, and we'll go from there. So Abe, all yours.
Good morning. Thank you, Jeff. So I'm going to talk a little bit about the DSOC system. DSOC will test groundbreaking technologies required for returning 10 times more data from deep space missions. The JPL has developed a system to demonstrate the first laser communications from beyond moon distances. In fact, almost 100 to 1,000 times farther than the moon. This system is comprised of a flight transceiver and also is works very cooperatively with the ground data system, which includes telescopes and instrumentation that Mira after me will talk about. Our technology demonstration will last for 2 years from the time of launch. And during that time, we will not be sending Psyche data back, but we will be evaluating the performance of the link and testing it in various ways. So what are the key challenges for doing this from the distances that we're talking about? We have to point a narrow laser beam from deep space back to Earth, back to an Earth receiving station, covering a distance of about 200 million miles, or about 2.5 times the Earth-Sun distance. An analogy for describing this is like trying to hit a dime from a mile away while the dime is moving. And that relative velocity between the hitter and the dime introduces something called a point-ahead angle. It's another analogy that I'd like to draw is it's like skeet shooting, but this is happening at a very, very large distance. And in addition to that, because of the large distances involved, the signals that are transmitted and received at either end of the link are very weak. And for that, we need very sensitive detectors and very accurate control. So the key flight technologies that are assembled are integrated into the DSOC flight transceiver are a first of its kind near-infrared laser transmitter. This transmitter is able to put out very narrow pulses of light, which are, by timing the pulses, we can encode information that then can be extracted at the receiver. In addition to this, laser is coupled to custom optics, which is like a traditional telescope, except it's customized to transmit and receive laser beam signals. And it's also equipped with very sensitive sensors, detectors, and actuators so that it can control the pointing of the laser beam. So the way that this works is we get assistance from the Psyche host spacecraft to initialize our pointing back to Earth. And of course, that involves interaction between the Psyche spacecraft software and the DSOC flight software. And but that's not sufficient to get the accuracy of pointing that we need to get the laser beam back to the receiving station. So what we do for that, and here's where the cooperative ground and flight interaction comes in, we send a laser beam from Earth up to the spacecraft to illuminate it. And within the course pointing that the spacecraft provides, the DSOC payload will find that beam and kind of lock onto it. And then from that point on, it can use that as a pointing reference to send its beam back. And of course, as I mentioned before, it has to point the beam ahead of where it's seeing the beam coming from. So for all that, the ground and the flight have to work cooperatively for this link to work. So for me, this has been a great privilege working on DSOC for a great number of years. What I particularly like about laser communications is its multidisciplinary aspect, where you get to meet subject matter experts from various fields and you're always learning something new. And so with that, I'd like to hand it over to Meera Srinivasan, who is our ground manager.
Thanks, Ravi. So I'm going to talk to you now a little bit more in detail about the ground side of DSOC. And like the flight side, the DSOC ground system also contains several innovative or first-of-their-kind technologies that were developed in tandem with the flight system to jointly demonstrate our technology objectives. And one of the, I think, unique and interesting things about this project is the fact that we have this ground component to deliver in addition to the flight terminal. So I think, as Jeff had mentioned before, most JPL missions don't have to do this. They take advantage of the existing ground infrastructure in the form of the Deep Space Network, which is a network of large antenna dishes that are used to communicate via radio frequency, or RF, to our spacecraft. No such infrastructure is already in place for optical communications. So as part of our project, we had to design, build, and retrofit our hardware both for this uplink laser transmitter and for the downlink optical receiver into existing telescope facilities that are located here in Southern California. And while this was challenging to execute all of this parallel development, it's nonetheless very exciting, and we're really looking forward to the fact that these same people who've built this hardware are going to soon get to operate it and run experiments with it, and we'll figure out in real time how to most effectively execute these deep space optical comm links and bring this technology to the same level of maturity, hopefully, as RF communications. So let me talk briefly about the three components to the ground system. So the first is the ground laser transmitter. So this is located at JPL's Table Mountain facility, which is approximately 90 miles or so to the northeast of JPL. And there we have a 1-meter telescope where we've installed an assembly of 10 lasers. And these are transmitting in the near infrared portion of the electromagnetic spectrum, so the slide is invisible to the eye. But we combine these beams to generate up to 5 kilowatts of power. And that level of power is needed because, as A.B. mentioned, at these far distances, we want this beacon signal to be visible to our flight terminal so it can use it as a pointing reference for the accurate downlink pointing necessary. In order to support this implementation there, we have to develop special optics that are capable of handling the high power levels involved. We have to develop special laser safety sensors and custom software so that we could automatically maintain alignment of these beams and shutter the beams when necessary. And so all of this together has come about, and we've done a lot of testing, and we're looking forward to basically trying this out soon. Now, the second ground terminal is the ground laser receiver, which is installed at the historic 5-meter Hale telescope at Palomar Observatory, which is in San Diego County. And this 5-meter telescope, it provides us with a large enough area so that we can collect as many photons as possible. So photons are the quanta of light that are, that arrive at the Earth from our flight laser over these long distances. And by the time it gets down to Earth, these are very weak signals. So we need to collect as many of these as possible. And as A.B. mentioned, information is conveyed in the precise arrival times of these photons. So what we have installed there is a superconducting nanowire detector array. So this is fabricated here at JPL. It operates at cryogenic temperatures that allow it to count these individual photons with very high efficiency. And in conjunction with follow-on specially built electronics, we're able to resolve the timing of the arrival of these photons down to the sub-nanosecond level, which is less than a billionth of a second. So, and this is what basically enables us to communicate very efficiently on the order of achieving 1 bit for every detected photon, approximately that order. And then finally, the third component of the ground system is mission operations, which is co-located with the Psyche mission operations here at JPL. And what we do here is we coordinate the activities of ground, transmitter, receiver with the flight terminal and with Psyche mission systems, so that together we will organize these passes, collect the data, evaluate it, and then determine how to make improvements and achieve our various objectives. So to conclude this, I'll echo what A.B. said, that it has been an honor to work on this project. It's the culmination of the work over the last few decades of numerous people here at JPL. And personally, it's allowed me to work on all stages from the concept development through implementation and operations. And we're very excited about this. So thank you, and I'll turn it back to Elise.
Great. Thank you, Mira. Thank you all for those comments. And with that, we will go ahead and begin taking questions. So again, if you are on the phone lines and would like to ask a question, you can do so by pressing *1. And while I give people a moment to get into the queue, I'll first go ahead and take a question from social media. This one, I think this will be one for A.B. This came in from X. The question I ask is, will there be applications for this DSOC technology here on Earth? So A.B., would you like to speak to that?
Yes, thank you, Elise. Yes, there will be applications of this technology to Earth. Like many of NASA's missions have always spun off technology that we use on a daily basis. And similarly, I think what DSOC in particular brings to Earth applications is the ability not only to count single photons, as was described by Mira, but also to count those photons with incredible timing precision, the sub-nanosecond or the billionth of a second that was mentioned. This brings a new capability that can be used for astronomy, for looking at time-resolved spectroscopy, for example, or things that are putting out pulses of light in space out there. We can detect those. It also has applications in spectroscopy, medical imaging, where you're dealing with very faint signals. Sometimes even if you're trying to image through the in situ imaging through the skin or through the skull, you can get enough photons. So all those applications will bring to bear, and yeah, so there's a host of applications out there.
Great, thank you, AB. And so we'll now go to some of our questions on the phone. So we can take our first question here from Ramin Skiba with Wired Magazine. Please go ahead.
Hi, thank you. I was wondering, is there a time, like a schedule planned for when optical communications would be the primary form of communication for a future mission? Like, are you planning, let's say, for a mission in 2030, 2035, any particular mission?
Thank you for that question. Jeff, is that one you'd like to take?
Yeah, sure. Yeah, and thanks for the question. I think from our standpoint, we're working actively with the Science Mission Directorate and with the Exploration Mission Directorate to talk about what those future applications might look like, right? So as I said, a lot of missions will continue to use RF communications. They don't need the capability that we can provide with optical, but there will be some incredible missions we can do with optical as kind of an enabling technology. So right now, I think we're counting on the DSOC mission, as Tanya described. These demonstrations are going to really give us a lot more insight into what does an operational system look like. And so I think, we're going to take what we learned from DSOC and continue to work with the scientists that are planning those future deep space missions to find that right fit and to kind of tune the technology to make it operational. So we're not quite ready for prime time. We need DSOC badly to kind of learn how we get ready for that operational use on a future mission. So TBD is the answer to that, but it's an active conversation.
Thank you, Jeff. We can take our next question here from Marcia Smith with Space Policy Online. Go ahead, Marcia.
Thanks so much for taking my question. I guess I'm trying to figure out what exactly it is that needs to go right and what could go wrong. In terms of a demonstration, you're not using this operationally on Psyche, I guess, because you haven't tested it enough. But what is it that you're looking for? What does it have to prove before you can actually use it in an operational manner?
Thanks, Marcia. AB, would you like to start with that one, and then others can jump in if they'd like?
Yes, absolutely. Thank you for the question. So there's different aspects, there's different phases, if you like. The first thing that we want to be able to do is to prove that on the spacecraft, with its sensors and actuators, can indeed detect and lock onto the laser beam that we're sending from the ground. I mean, that would be a big enabler, because without that pointing reference, the rest of the operations doesn't work. So that's the first step. And then once we do that, then of course is pointing the laser back to Earth. Now we have the pointing reference. We have another control system which does the point ahead and all that. So we need to prove that we can use the received laser as a pointing reference and transmit a laser beam, some point ahead angle away and hit the ground station. That's the second sort of major milestone, I would say. And then finally, when the photons are received on the ground, we have to do the real-time signal processing, with the timing and measuring the timing of the pulse arrivals and then decode that. And of course, we have very powerful codes, and a lot of this has been extensively tested on the ground, but we still need to do it from space with the atmospheric channel thrown in between. And so that will be another, in my opinion, that's the least difficult of the three things that I mentioned, but that is also key to getting the information back on the ground.
Hi, this is Tanya. If I could just add on to kind of maybe give a philosophy answer to that question. I think the point of us doing this really is to fly technology, to demonstrate the technology that has a transition path, so it won't be used. And so that will be used and not just sit on the shelf. To me, you only have a failure if you don't get the data. If you get the data, but the technology didn't perform as you expected it to me, that's not a failure in the research and technology development. And when you're pushing the envelope like we're doing here, you're going to try things that haven't been done before. So even if the technology doesn't perform as expected, you're still going to get new data, and you're going to learn by looking at that data. And so you may find out that a certain technology was not the direction that you wanted to go, and then you just go into a different direction.
All right, thank you both. As a reminder, if you have a question, you can get into the queue on the phone lines by pressing *1. And we'll take our next question from Stephen Clark with Ars Technica.
Thank you. I think my question is probably for Aby or Mira. Can you talk about the size of the footprint of the beam that's coming down from DSOC when it reaches the Earth, and just how much margin for error do you have in the precise pointing that you need to establish and lock onto that link between the ground station and the DSOC terminal in space? Thanks.
Please go ahead, Aby. Thank you.
Yeah, thank you for the question. Yeah, so that's a great question. So, as I said, the laser beam is very narrow, and we measure it in angular units. But without going too technical, the footprint when it reaches Earth is of the order of, at the very first time when we turn DSOC on, which is about 16 or 20 days into the following launch, it will be about 75 to 100 kilometers. By the time we get to the farthest reach, which is about 2.5 the Earth-Sun distance, it will be about 1,000 kilometers, about the size of the state of California. So that's the size of the beam. Now, in terms of how much error tolerance do we have, I mean, you're measuring a very small angle, but from a very large distance. So there's a huge lever arm. So, for example, if you're off by, let's say, some thousandth of a degree or something, then your beam footprint is somewhere over the Pacific Ocean, and the ground receiver at San Diego County is seeing nothing. So that's the kind of pointing precision. So we like to talk about it in microradians. So we have to point to within a few microradians. And so that's the kind of tolerance. So in order to make sure that we hit the target, we have techniques that we can scan the beam over some uncertainty space, so that in one of those positions we'll with a very high likelihood hit the ground receiver. So we've got those things built into our software and capabilities.
Thank you, Aby. All right, we can take our next question. This is another one that came in on social media. We've actually had a couple on X asking us what sort of speed you're hoping to achieve with this technology, or what is the bandwidth compared to laser comms closer to Earth? So, Aby, is that another one you'd like to jump in on?
Yeah, sure. I'll take that. This is Mira. So, in terms of the data rates that we're talking about, we can range from hundreds of megabits per second near Earth, all the way out to hundreds of kilobits per second at our farthest range. In terms of the actual bandwidth, actually, Aby, maybe you could address
that. So in terms of the optical frequency, which is the bandwidth, is about 280 terahertz. Just to give you a point of reference, the radio frequencies that are used are in the tens of gigahertz. So it's orders of magnitude higher in frequency. And that's what allows you to pack a lot more data into this beam.
Thank you both. We have another one here, and Aby, you discussed this in your comments, but maybe you'd like to elaborate a little bit. This one also from social media, asking about some of the challenges to laser communications in space compared to radio frequency, and that could be one that Jeff, I think, could jump in on as well.
Thank you for the question. So there are, what optical or laser communication allows you is to achieve very high data rates. But on the downside, it's a very narrow laser beam that requires very accurate pointing control. So for example, the platform disturbance from a typical spacecraft would throw off the pointing, so you need to actively isolate from it or control against it. So for near Earth, for example, missions, you can just control against it because you have enough control bandwidth. From deep space, where the signals received are very weak, you don't have that much control bandwidth, so you have to isolate from the disturbance and then control at a lower bandwidth. So that's one of the challenges. Of course, when you compare it to RF can communicate through clouds and things like that. For optical, we have a cloud blockage problem. So, so for the tech demo, we have scheduled enough opportunities that with Southern California weather, we expect to get enough opportunities to do the work that we need to do. But for a future operational system, you'll have to have ground stations distributed around the globe so that you get weather diversity, so that at any given time, there's a very high likelihood that one of the ground stations will be able to receive data from space. So that's one of the workarounds you need. Another different aspect between RF and optical is RF communications. You can have omnidirectional antennas in RF so that if the spacecraft goes into a safing mode or an emergency mode, then the RF can help you recover from that. Optical is not there yet. We do not have omni antennas in optical. So even if we flew optical on a mission, we would need at least the RF omnis for emergencies.
Yeah, this is Jeff. I could add a little bit. That was a great answer. I can only add a little bit more to that. And the part that I'll talk to is mission acceptance. So demonstrations are key to getting mission designers to think about how they might insert a technology operationally. And they're going to want to have answers to questions like reliability. Will these lasers last long enough if I'm going to be flying a deep space mission that might last for decades? They're going to want to know about the cost of the units and how hard they are to produce. Are they commercially available, or does each one have to be developed and built by the government and takes more time, right? So these are all the things we're doing in addition to doing the demonstrations. We're trying to move this technology into commercial industry where they can provide units that Northrop Grumman or Lockheed or Boeing or any of the vendors of spacecraft, be they large or small spacecraft, can have an opportunity to go off and buy them commercially to fit on their spacecraft. And the other part is that when you put this on a spacecraft, it's great to have a communication capability that can bring data to Earth so fast. But do I have a spacecraft that has a computer and solid-state memory where it can read the memory fast enough to feed this incredible optical communication capability? Our deep space missions to date have never had this kind of capability. So the designers of the architecture of the spacecraft have never had to design the faster ability to read off a recorder, to store more data. Similarly in Earth orbit, we're going to be maybe working, as was mentioned, very high data rates. I need a whole spacecraft design now that can take advantage of that I can store hyperspectral data from sophisticated cameras and then quickly read it off to an optical terminal. So I think moving from demonstration operations includes all the things that Amy said about the technology itself, as well as getting to this mission acceptance through commercialization of the technology and making it available to the vendors that build spacecraft and having them architect around using an optical to take a full advantage of what it can bring.
Thank you both. We can now go back to another question on the phone. This is another question from Stephen Clark with Ars Technica. Go ahead, Stephen.
Hey, thanks for taking another question from me. Just wondering if someone could answer my question on what is the total cost of this DSOC flight experiment. And if I may, also, once the demo phase is over, is there any possible plan or any technical means to relay any science data from the Psyche mission through the DSOC system to get that data down to Earth quicker? Or once you complete this demo before arriving at Psyche, is DSOC done? Thanks.
Thanks, Stephen. So for the first, I was going to just toss to you, Tanya, for the first part of that question. Please go ahead.
Appreciate it. So the cost for developing and operating DSOC is about $206 million.
Okay, thank you, Tanya. And for the second part of that question, Mira or Aby, is that one you'd like to address?
Yeah, so right now we're really focused on our primary mission, which lasts for 2 years, which is a fairly long time and a weekly cadence. There has been no discussion of, extended mission, though whenever missions are successful, even tech demos are successful, it's not unknown for them to extend into, extended mission phase. So we just have to wait and see. I mean, right now we're really focused on our primary mission.
We do have the capability, however, of interfacing with Psyche and receiving data if that comes up.
Yes.
All right, great. Well, thank you all so much for those responses. That is it for our questions and our time today. But thank you very much to both our speakers and to everyone who tuned in. If you do have follow-up questions on DSOC, please do reach out to us, and NASA's media team will be happy to help. And we hope you all follow along with this upcoming launch. Again, as we mentioned, DSOC is flying on the Psyche spacecraft, and that is set to launch October 5th. So to learn more about Psyche, the DSOC tech demonstration, and to stay updated on the launch, you can visit nasa.gov/Psyche. So thank you all.
Thank you. And that concludes today's conference. You may all disconnect at this time. Speakers, you may stand by for a post-conference.